As he said, my name is Sigurd and I'm an exchange student from the University of Oslo. And I will be talking about how I leverage APIs to power an autonomous surface vessel this summer in my internship. So first, a little bit, who am I? I'm from the University of Oslo, as I've said, and I worked at the Kongsberg Group this summer as an intern. And here you can see the logo of Kongsberg, and also two of my projects I did last semester, which were both group projects. I built my own operating system, and also I built an AI-based fishing guide, which was actually nominated for an award by the Meteorological Institute of Norway. Just as like a general introduction, I'll be speaking about geospatial APIs, how to decode the data you get from the APIs, and also more specifically actually how to decode certain types of coordinates. I will be speaking a little bit about DCLs. I don't know if you are familiar with them, but I won't go into them too deeply technically, but it stands for domain specific language. And also I'll be speaking a bit about AI APIs. So first I want to introduce the project I worked on this summer. We were 8 students working on this boat. As you see, it's called an USV, uncrewed surface vessel. We basically got the task to make this autonomous, to map the seabed of our fjords. And we did this in collaboration with a project called Frisk Oslofjord, which means healthy fjords, basically, because of the bad environmental state our fjords is in right now. And you see the USV here, it goes on top of the water, and it has a sonar. It's the red thing you see. It's like it's what actually could collect data from the seabed. And we also have a underwater ROV, which could be deployed from the boat that goes underwater with camera. We also have a UAV that could follow the boat position to like scavenge or something for the USV. There you can see a video of the USV from a live mission. This was with a marine biologist which needed to collect data about the seagrass in a fjord, because seagrass is a good indication of a healthy fjord. So she basically wanted to map the areas where seagrass were. Okay, so here comes my responsibility this summer. I was basically told, Sigurd, you are in charge of mission planning. I was like, okay, what really is mission planning? Mission planning is basically planning the mission. It's deciding where the USV goes and making a path for the USV, which that USV obviously can follow autonomously. And basically what I got was this. I got an USV on a map. And how could I do planning based on this? The normal way would be to draw your own polygons and create like a lawnmower pattern inside that polygon. But both me and my boss thought that would be a bit boring, basically. So he's told me why don't you pursue some sort of AI solution that could understand the position of the vessel to give feedbacks and actually generate missions. And then I was like, yeah, it might probably be possible, but you could have an AI which could actually interpret this picture, go pixel by pixel, check what is water, what is land. But you probably have a solution where you have to pre-upload documents and stuff, which is not really dynamic, not really cool. So I was like, how can I leverage APIs here? So I was like, what sort of open source data could I get from the fjords or the water? I was like, probably I would be able to fetch the depth in a certain area. So I did that. I fetched the depth and got depth data points. Then I tried to make a polygon based on those depth points, but I was not able to don't make them cross over land, because they didn't know what was land, they only knew what was depth points, basically. So then I was like, I need to know where land is, because I can't send the USV on land, right? So then I was like, probably the coastline could be useful here. So what I did is that I fetched the coastline, inverted it to make a water polygon, and then with the depth polygon I already had, I intersected it with the water polygon. So I was left with a 100% safe water polygon, which you use with Good Survey. So now I'm going to talk a bit about the technical side, how I managed to do this. So first I want to just introduce the tech stack. I don't know if a lot of you are familiar with it, but I use Kotlin as the main programming language, which is a language used to write Android apps. And I use Android Studios as an IDE, it's the main IDE to build Android apps. It lets you run, test, and build Android apps on an emulator. And then I use Mapbox, which is a map service which lets you add interactive maps to your applications and display certain data. So how did I find the APIs? There's like tons of different ways to find APIs. You have like public APIs, it's a GitHub repository with like 30,000 open source APIs. And you have public APIs.io, which has like 1,500 open source API, which you can have like a search bar and search through them. You can use Google, of course, and you can monitor the network traffic, as I'll show you later. So here you can just see the public APIs.io, and you have like so many different APIs. Here you have like, you can fetch like mugshots, or like have web scrapers or AI agents. It's crazy. And here I show you where I use a developer tool, the inspect function on a website, and I switch to the network tab, and I can basically monitor the traffic between the website and its backend to check what sort of API calls they do, and then I can basically steal them almost, right? So what I needed for my phishing app, right? I needed phishing spots. And there was no open source phishing spot APIs in Norway. So I was like, I'll just check some of the phishing apps that exist, and I just monitor the traffic to find their APIs. And then obviously I ask for permission to use it. And just a little bit about diagnosing an URL, right? What you get from what I just did is quite messy, right? But as you can see, if you just highlight certain areas, it becomes quite simple. So you see the text in a polygon. And then you could like imagine, okay, I get the phishing spot within that polygon, and it has like a limit and order by and stuff, which you have to get familiar with to be able to understand the data you get. Because I just wanted to fetch every phishing spot in Norway, right? But it had a limit of 200, so if you're not aware of this sort of stuff, you can get into a lot of problems. Then I will talk about geospatial APIs, mainly how to decode coordinates, how to actually render the APIs, render the polygons or the data in your application, different use cases and challenges. So here you see a few different coordinate systems. As you can see, they are not compatible and they don't work together at all. But when you use a lot of different APIs and also a lot of different softwares, all of them require different sort of coordinate systems. So therefore you have to project the coordinates you get into another coordinate system. As you can see here, I project from one certain coordinate system, EPSG something, to another one, with the use of a library called ProJ4J. It's quite simple. And also, stuff you should be aware of is that you could actually specify the coordinate system which you want in your URL call. So therefore you don't even have to decode them, but not all APIs have this, of course. And then the rendering. Because the data you get is quite messy, right? You get just like thousands of coordinates and you don't really know how they work together, and it's quite hard for the human eye to just identify everything you get from the call. So as you see here, when I actually fetch the coastline, right? I fetch the coastline, and then I also fetch the islands within that coastline, and those islands became holes in my water polygon, right? And I just weren't able to draw these holes at all, which was so frustrating. But I found out that the holes were never closed. The first point has to equal the last point, right? For a polygon to be able to be drawn. And that's what you can see here. You can see that val closed. Basically, if the first and the last coordinate isn't the same, just add the first to, at the end of the list, and you have a closed polygon. It's like stuff like this you have to do. You have to clean all your data before you actually render it. And then after you've done this, you are ready to actually draw it on the map. I just want to speak about a few use cases. You could do like mission and route planning like I did, and navigation and guidance. And you can do geofencing, for example, if you have a drone project, you can just fetch like airports in the area to try and avoid them, right? Or you could do environmental monitoring, monitor the different sea levels and stuff. You know, they always talk about the sea level rising. And you can do asset tracking, which is really cool, because most boats over 25 meters are publicly, their position is publicly available through APIs. So for example, you could like just showcase the maritime traffic in the harbor of Singapore, for example. And you could do like, because this is in real time, you could like try and fetch their path over time, and maybe like try and make their path better or stuff like that, do optimizations. You can use it with AR and VR. Instead of using machine learning to actually understand what you see, you can use like, if I'm at this certain position in the world, facing this direction, what should I see, right? Fetch like famous places, APIs and stuff like that. And you can also do disaster simulation, which is really cool. And you can like, if you fetch the height curvature of a certain place, you can like see how heavy rainfall will affect certain areas, or like a tsunami or stuff like that. With challenges with geospatial APIs, I've touched on some of them, but you get like huge feeds, right? When I fetched my fishing spots, the spots were polygons. It was like areas in the water where this certain species existed. And I got 30,000 spots along the coastline of Norway. We have a really long coastline. And all of these spots were like 10 to 15 meters in the real world, right? But they were made out of 50,000 points each. So like a 10 to 15 meter polygon made out of 50,000 points is like, has extremely much overhead, right, and so unnecessary. So I just divided the amount of points 10 times, or I think I did it like 1,000 times almost, and kept 99% of the accuracy of the polygons. That's stuff like that you gotta do if you use geospatial polygons. And also when you use open source API, you have no demands to their usability, right? For example, you can't be promised no downtime, right? It would be quite crucial if your application stopped working because some certain API has a downtime. And also debugging all this huge raw data is quite hard when you have so much just coordinates, right? It's super hard to debug. And now that I've like actually been able to compute water polygon, safe water polygon with APIs, I needed a way to get the user's intent, right? I could like make the user just like fill out a few parameters and then generate the mission, but I wanted to actually automate this part as well. So what I did, I wanted to go from natural language to a path as simply as possible. And to do that, I used an OpenAI API and also a DCL in between, which I will touch on later. So first of all, I used an OpenAI APIs. I basically built a ChatGPT wrapper, which I let the user write a prompt, and then I basically sent that prompt to a ChatGPT, with the prompt being, what does this user want? But then it was like quite hard to, because if you have sentence monitor Singapore, right? You can't programmatically understand the substance or verb of that sentence, right? So that's why I used the machine learning. But what the AI actually was going to output was like a bit hard to find out on my part. So therefore I was like, what if the AI outputs my own domain-specific language, right? Because a domain-specific language, you build it yourself, so you can make it look almost identical as natural language, but not 100%. So you can like see a few examples here. You like survey Oslofjord, right? It's the Oslo fjord, and then monitor a polygon would be the DCL, and that again that could then become executable code. So here you see AutoScript, I call the language. Here you can see the syntax and also how I built the grammar, or just a small part of the grammar. It's like, as you see in the top, it's like script is defined as a statement. It could be multiple statements. And then again, statements is could be multiple different things. And all of this builds like a big syntactical tree, right? And what you can do when you have this tree is that you can parse it and interpret it yourself, right? Because you built the language. And the added benefits of this is like, as I've mentioned, that it's much closer to natural language, so it's much easier for the AI to translate something to this. Because as you saw on the last slide, this language would translate about 1,000 codes or lines in Java, right? But going straight from the AI to those 1,000 lines of code in Java is almost impossible. But if you add the layer in between, like a DCL, you could also do type checking yourself. You can check that the coordinates is the right type. You can check that you don't have any weird negative values and stuff like that. And it's much more readable for a person and also for an AI. And it adds like an abstraction layer between AI and executable code. It also works like a safety layer, right? And now that I've had like, I can write a prompt and get a water polygon and then mission. Now I need to actually make a path within that polygon that I have computed, right? So first of all, I just want to showcase some general how path planning works. So I show on the whiteboard. Just a simple would be that you have a polygon right like this, and you just smack on a lot of lines like this, which is evenly spaced, and then you connect them, right? So now we have a path in that polygon. But since my polygons could be quite complex, right? It could be like stuff like this, right? It would be quite hard to actually know the best angle of these lines. Because let's say you have this polygon. You don't want to go like this, right? You want to go like this. So you minimize turning, because turning can be quite expensive at sea, right? So therefore I used principal component analysis, which I don't know if any of you have math for AI this semester, but we just learn about it. It's pretty cool. It's a way of finding a direction of a certain data set. So you find like the middle, and then you compute the difference with all the points to this middle point along the x-axis, along the y-axis, and along the x-y-axis. And then you basically use all of these three to find the general direction of the polygon, which would look like something like this, kind of, right? As you will see later in my demo, I will show you how this worked. But also you have to do dynamic planning, right? Because things at sea isn't always what it's supposed to be. Like, for example, if you have to avoid something to avoid collision, right? You will have to catch up with where you left off in that path. So you have to always replan the path planning. And that works like as you remember the path that you have already done, and you always compute the next one. But unless something happens, the next one will just stay the same. But when something happens, you are ready with the new path, which would then be minus the one you already have taken, right? And you could also do replan based on a point of interest, right? Since you map the seabed, if you find something interesting, for example, like an area where the depth had a sudden change, or an area where there was a sudden change in the hardness, for example, or it went from gravel to sand, something like this, we could replan based on that point of interest, which is pretty cool. And now I've talked about all the technical sides and how I managed to do this, and I will show a video of how everything is knitted together. So you write the prompt, right? Like generate a safe survey area for the USV. And it will fetch the coastline and the depth points to make polygons like this. Then it will compute a path within that polygon. And what is pretty cool, I think, with this is that it simulates advanced AI, but really it's just basic API usage in the backend, right? And since our sonar works like a flashlight, right? The deeper the water, the bigger the coverage of the seafloor. Therefore, since we use the API, we already know the depth of where we're going. So we can plan based on the depth. Because if you know the two green lines, basically, and you know the angle of the sonar, you can find the red line, which would be the coverage. And that will look something like this. That you adaptively choose the line spacing to make a more optimal and efficient path. And just imagine you would do those small lines the whole way, right? It would take like 80% more time. So here you just use simple physics to save a lot of battery and a lot of time. So that was basically my talk. Thank you so much. Any questions? Yeah.
How have you compared the solution you've created now that there's something like scale with Gaia by Visa as well? Have you heard of these two companies?
No.
Have a look at Scale AI and Visa. So they are both generally geospatial analysis platforms rather than that may be something we want to consider. Another thing that I was thinking of is when we talk about the angles that we're considering, has there also been considerations on buoyancy and currents against the seas at that point in time? That also changes with different seasons. Just wondering if that was covered.
Yeah, actually, the current part that you mentioned, right? It's something I hope to do next summer. And that also is very easily done by APIs, because you could fetch the currents in a certain area. And if a mission could be everywhere from 1 hour to 3 days, right? The current could change quite a lot. So you can save a lot of time and energy on computing the path based on currents is very important. And like a lot of hydraulics and like turning against the currents and stuff like that, which I'm not expert in, but like there's a lot of cool stuff you can do with the currents, right? Yeah.
Sometimes the best option is to actually not go out to sea. So
Yeah, that's true as well. We had a weather warning in our app, for example.
but yeah, check out Scale and
Yeah, cool.
Sorry.
Yeah, sorry.
I might have missed it, but any plans for iOS?
Oh yeah.
Carry on, my bad.
Yeah, so Android Studios and Kotlin is like an introduction to app building, right? It's very simple to use. but 1 year ago, Kotlin 2.0 just came 1 year ago, and it's supposed to work on iOS, but I never tried it myself. But in theory, all the code should work in an iOS environment. So, yeah.
This one.
Was-
Yeah, I was wondering, how hard was it to get the AI to understand your custom data and whether you encountered any issues?
So basically, for my AI to understand my DCL was super simple because the DCL was so simple. So I basically only did augmental retrieval learning. So I sent a big prompt, which was like 3 examples of the code, and just returned something along these lines, basically. And the only thing it really tried to fetch from the user was the place it wanted to do something and what it wanted to do. So for example, if you wanted to do waypoints, it would have had a different functionality. For example, monitoring or surveying would be more like a mapping-based pattern. So it's super simple. Also, I've added that you could choose the distance to shore with the polygons in the prompt. And also added that you could choose the minimum depth as well. And also added a few different things that you could fetch as just some cool stuff like seagrass in a certain area and stuff. Like, because that was what we mainly tried to map, was seagrass areas. Yeah.
I'm not technical student, so I think I missed out, or maybe I did not catch the point. Just now mentioned about collision avoidance, and did you see half in this presentation, but how does the current solution, how does it prevent the collision?
Okay, so
I understand there's like this path, right, this path better. Then what if suddenly like the vessel does this path?
yeah, so that's why we have radar and a camera cluster on the boat for collision avoidance, to not hit something, right? And that was why I talked about the replanning, because if you try to avoid something, you will go off course to try and avoid it maybe. So then you have to replan the new path based on where you went off course and stuff. So in actually avoiding obstacles and vessels, apart from land, I don't use APIs at all. It's only the radar and camera we have on the boat.
So you mentioned that you use custom DSL to, you want the AI to generate your custom DSL, right? And it is because it is a simpler format and it's better for LLM to generate because it's more similar to natural language.
Yeah.
So I assume that's the reason why you picked it over JSON. Because JSON, we have a lot of like existing libraries that help you do all the structured validations. So I'm curious, how much better does LLM perform using DSL as compared to JSON?
Basically, it has so much built-in parsing functionality. Like you said about the libraries with JSON, would probably be a quite good solution, right? But also, if there was, for example, you wanted to build on this language and add like 2 different missions in one program and stuff, it would be harder to do so in a JSON, because it would be basically harder to try and basically what the AI outputs and what AI is capable of is harder to fit into something so broad as a JSON than to something so simple as an DCL. Not really the syntax, but just like the DCL can only be 3-4 different things, right? But the JSON can be unlimited long and stuff like that, you know. So that was why I chose the DCL.